All right. So today we have the pleasure of receiving here in our current installment of the of the mono webinars, Dr. Vinicius Carvalho from the Oswaldo Cruz Institute, Oswaldo Cruz Foundation, and I will invite Lucas Bolini for this presentation. And today is also the last talk that we are going to have in the first semester of 2024. And we will return at some point. I'm not sure if we have the data ready, but we will return at some point after a few weeks break. So, Lucas, if you could please make the introduction of our guests today.
Thank you. Good afternoon, everyone, and welcome to, as Bruno said, our last edition of Immuno webinars for this semester. Today we have the honor of having Dr. Vinicius Frias. Vinicius graduated in biology at the same University of Rio de Janeiro. He is a master in cellular and molecular biology by the Oswaldo Cruz Institute. He's also a doctor in pharmacology by the Federal University of Rio de Janeiro under the supervision of Dr. Patricia Silva, after which he had his postdoctoral period in the University of Nottingham in England. Currently, Vinicius is the vice head of the Laboratory of Inflammation at the Oswaldo Cruz Institute. He is also a member of the board of the Brazilian Society for Pharmacology and Experimental Therapeutics. He's also the coordinator of the Network for Metabolic Diseases and Aging from FIOCRUZ in collaboration with CAPES. He's also the coordinator of the Translational Network of Research in Metabolic Diseases and Aging from FIOCRUZ. And he also has an incredible body of work with almost 30 research papers published only in the last 5 years. So thank you, Vinicius, for accepting our invitation, and the floor is now yours.
Thank you, Lucas, for the great presentation. Thank you, Bruno and Miriam, for the invitation. It's okay.
Bruno.
Can you hear well there?
Ok. A apresentação voltou, mas o som eu não estou ouvindo.
Tô sem som.
Alô? Ouve agora?
Agora sim.
Sim, sim.
Let's go.
Okay. Okay. Can you hear me? Sure.
Baixinho, mas dá para ouvir.
Okay, I will talk higher with my voice. Okay, first of all, I would like to thank Bruno and Miriam for the invitation. It's an honor to me to stay here in the Institute to talk about one of the projects that I lead in the Oswaldo Cruz Institute. And today I will talk to you how the inflammatory pathways imbalance can modulate the adrenal production by in the murine model of diabetes. I'm sorry for this mistake here. Okay, first of all, diabetes is a chronic disease characterized by loss of carbohydrate metabolism, homeostasis, that culminates in the development of hyperglycemia. And we have two major types of diabetes. The type 1, that is related to a loss of beta pancreatic cells because of autoimmune reaction, or a type 2 diabetes is related to insensitivity of the insulin receptor. But both of this case culminate in the hyperglycemia and with the alteration in protein and lipid metabolism. The diabetes is a high incident disease in all the world, in all of the age, especially the older people in type 2 diabetes and the young people in type 1 diabetes. And one of common characteristics of both diseases is hormonal imbalance that occurs because of the fail of the production or action of insulin. And the hormonal imbalance is characterized by the differences in the production of several hormones, including the glucocorticoid hormones. And the diabetic patients present hypothalamic pituitary adrenal weight dysregulation with an increase in the production and release of glucocorticoids by adrenal glands. And we can attest this to measure the cortisol in the blood and the urine of diabetic patients. And several murine models of diabetes reproduce these characteristics, that hyperactivity of HPA axis and the spontaneous diabetes and the chemical induced diabetes. Okay, and what is the importance of the increase of glucocorticoid levels in diabetes? You can see in this picture that diabetes induced uncontrolled or poorly controlled glycemic diabetic patients presents several complications or several morbidities related to or causally related to hyperglycemia. But some of these complications or morbidities, now we know that is related to increase of glucocorticoid levels too, like such as the increase of Alzheimer's diseases and depression and the antidepressive resistance treatments, osteoporosis, wound healing deficiency, and neuropathy. Some of these complications are also related to increase in the glucocorticoid levels. And the glucocorticoid is produced by circadian and ultradian fluctuations production. This is an example of mice circadian fluctuation. And you can see that in the mice, we can see the increase in the production of the circadian levels of glucocorticoids is related to the active phase of the clock circadian levels. But you can see here that we have a peak of several ultradian levels of glucocorticoid production related to stress situations, because glucocorticoid is a stress hormone. Okay, and we can see that in the inflammatory response, we have several phases of this response: the acute, chronic, and the resolution phase of inflammatory response, and that the resolving mediators are high producing after the pro-inflammatory insult to the aim of resolve the inflammatory response. One of the resolving mediators, the important resolving mediator, is the glucocorticoids. And it is expected that after an acute inflammatory response, we have a high production of glucocorticoids to help to the resolution of inflammation. And the glucocorticoid is produced by adrenal glands. Not all the glucocorticoids produced by the adrenal gland, but most of the production of glucocorticoid is in the adrenal glands. And the blood glucocorticoids is related almost 100% by the production by adrenals. And in the clock circadian rhythms or after one stress situation, we have an activation of the hypothalamus, and the hypothalamus produces CR8 that will activate pituitary glands to induce to release ACT8, and the ACT8 is the master mediator to induce the glucocorticoid production in the normal situation and in the clock circadian production. And the glucocorticoid is produced by the zona fasciculata of the adrenal cortex. And we have two kinds of glucocorticoids. Cortisol is the most glucocorticoid produced by humans, and corticosterone is the most glucocorticoid produced by rodents, like especially rats and mice, because hamster, we see more production of cortisol than corticosterone. And the ACT8 will induce a glucocorticoid production by activation of its receptor in the adrenal gland called MC2R. And this receptor will activate the cyclical MP pathway, and this pathway will induce the high expression of the STAR, and this STAR will induce the intake of cholesterol to the inner mitochondria. And in the inner mitochondria, we will have the processment or the metabolism of cholesterol until corticosterone or cortisol, depends of the patients or model with mice. And we have some limitant enzymes like CYP11A1 and CYP11B1. This is important to the corticosterone producer. But we have another pathway in adrenals that is important to corticosterone producer, that corticosterone will produce by 11-dehydrocorticosterone. This is induced by HSD11 beta 1, okay, that produces the inactive cortisone, inactive corticosterone. This pathway is more studied in the peripheral tissue, but this pathway is also important in adrenals too. It's a secondary pathway to the corticosterone production. And we and other authors published prior that in diabetes, the hypercorticolism or hypercortisolism is induced by two ways. Hyperactivity of the ACT8 axis, okay, with high production of ACT8 and a high expression of its receptor in the adrenal cortex, and also by an impairment in the negative feedback of the HPA axis, because this axis is finally regulated by the own glucocorticoid to avoid the side effects in the metabolism of corticoids. And we show it that there are a reduction in the expression of both receptors of glucocorticoids, GR and AMR, in the pituitary glands, and almost in the pituitary is the mechanism for the impairment of negative feedback of HPA axis. And today, the aim of the result that I brought here is to evaluate whether inflammatory pathways can be involved with the overproduction of corticosterone by adrenals in diabetic mice. We used a model that type 1 diabetes induced by alloxan. Alloxan is a glucose analog that will have a great selectivity to the beta cells and short half-life. And we observed beta cells lesion, after alloxan treatment in the animals, and a reduction of insulin biosynthesis. And we can see a diabetic state. And I can call attention for you that this model is not a good model to study the onset of diabetes, onset of type 1 diabetes, because it's not an autoimmune response that alloxan induced, but it's a great model to study the several complications related to diabetes. We can see polyphagy, polydipsia, polyuria, increase in the drinking water, and the loss of weight. We can see neuropathy, nephropathy, several symptoms related to diabetes with this murine model of diabetes. And in the beginning, we think in the study the effect of PPAR gamma in this model, because the PPAR gamma is an anti-inflammatory receptor and a receptor involved with lipid and glucose metabolism. Okay, and PPAR gamma is a nuclear receptor that's active binding in the DNA and is involved in the metabolism, like I said, but also in the inflammatory response. And the activation of PPAR gamma shifts the inflammatory response to an anti-inflammatory pathway. And we treated the animals with PPAR gamma agonist, rosiglitazone. All our treatments, we used 3 or 7 days after the diabetes induction. And in this time, 3 or 7, we have a hyperglycemia, reduction of insulin levels, and increase of glucocorticoid levels. And first of all, we looked for the number of PPAR gamma positive cells in the adrenals. And you can see here a decrease in the cells positive to PPAR gamma. And rosiglitazone is an agonist, and it is very well known that rosiglitazone induces an increase in the expression of PPAR gamma. And you can see an increase in the expression of PPAR gamma positive cells in the zona fasciculata of adrenal of diabetic rats. Okay, and then we looked for the production of glucocorticoids, or the levels, the systemic levels of corticosterone, and the possible pathways involved with the activation of PPAR gamma. And you can see here an increase in the plasma corticosterone levels in the diabetic mice. Rosiglitazone decrease significantly restored the plasma corticosterone levels. And when we treated the mice with rosiglitazone and GW9662, the PPAR gamma antagonist, you can see that the antagonist reverses the effect of rosiglitazone. Reverse now, blocked. Yeah, thank you. Blocked the effect of PPAR gamma. This, because of this, we know that the effect depends of the activation of this receptor. And you can see here a great expression of ACT8 receptor in the adrenals that was reversed by the rosiglitazone treatment. Okay, and we believe that the effect is to inhibit the ACT8 pathway. And we can see also that we have a reduction of ACT8, plasma ACT8 levels, and the rosiglitazone blocks indirectly blocks the ACT8 induced corticosterone production. Okay, And as the PPAR gamma is involved to insulin signaling and the PI3K pathway, we will look to the PI3K P110 alpha expression. Okay, you can see here there is no difference in the expression of PI3K in diabetes. However, you can see, not however, but you can see that the treatment with rosiglitazone increases the expression of the PI3K. And when we co-treated the animals with vortmannin, that is a compound that blocked PI3K, you can see that vortmannin partially restored the production of corticosterone by adrenal glands of diabetic mice in the presence of rosiglitazone. And we can conclude here that our results indicated that activation of PPAR gamma normalizes the capacity of the adrenal of diabetic rats to produce corticosterone by a mechanism related at least partially to a revolution of PI3K. Okay? But another pathway that we will look at was the renin-angiotensin system, because diabetic patients present a high activation, hyperactivation of renin-angiotensin axis as HPA axis with a great amount of angiotensin II, and the angiotensin II production inhibition is related to a reduction of several complications of diabetes like neuropathy, wound healing deficiency, that was correlated to the hyperactivity of HPA axis. And as the angiotensin II is a pro-inflammatory stimuli too, as a pro-inflammatory stimuli here, okay, is also a pro-inflammatory stimuli, we think that could the high amount of angiotensin II in the plasma of diabetic mice evolved to the hyperactivation of ATPase and the overproduction of corticosterone by adrenals. And here I will remember to you that angiotensin II is produced by angiotensin, the effect of renin, and more important for us now today here, the ACE2 is a major enzyme, the ACE, I'm sorry, is a major enzyme involved to the conversion of angiotensin 1 to angiotensin II. And angiotensin II can active A2-1 receptor, it is a pro-inflammatory receptor, is more affinity to A2-1, but can be activated other receptor 82 that have anti-inflammatory properties, okay? And we will modulate here in the ACE, in the A2-1 and A2 receptor, the animals in this project. And why we will look for angiotensin II also? Because angiotensin II is also involved with steroidogens. Okay. I told you that ACT8 can activate epithelial cells in the zona fasciculata to induce glucocorticoid production, and it's well known that, I'm sorry, aldosterone, no, angiotensin II, I'm sorry, I don't know why aldosterone is here, but, I remember. Because angiotensin II can induce the aldosterone by zona glomerulosa of the adrenals. But angiotensin II has receptors in the zona fasciculata and can activate the same molecular platform, signaling molecular platform than ACT8. And some papers published that angiotensin II can induce corticosterone production. Okay. And then first we block this using captopril, treating the animals. And you can see here, and here diabetic animals, here non-diabetic animals, and here diabetic animals treated with captopril. And you can see first that captopril reduced the glucocorticoid production by adrenals. You can see a great reduction in the plasma corticosterone levels. And this was the pathway mechanism that we looked in the steroidogenesis was depends of the reduction of ACTH receptor on the beta HSD1 is the enzyme that I told you that converts cortisone and corticosterone, and a reduction in the STAR, the enzyme that induces the intake of cholesterol to mitochondria. And the captopril works as an inhibitor of ACE. You can see here that captopril significantly decreases the plasma angiotensin II levels and restored to the normal levels. And then we will confirm if this effect, we can reproduce this effect with 81 blocker. We choose for the olmesartan because until we know and until we published this paper, the olmesartan was the only H1 blocker that does not works as a PPAR gamma agonist. Okay. And you can see that the effects of olmesartan was very similar that we observed with captopril. Reduction of the plasma corticosterone levels and reduction of ACTA receptor expression, 11 beta SD1 expression, and the SAR expression in the adrenal glands. And then we will look to expression of angiotensin receptors. And you can see that in the adrenal gland of diabetic mice, an increase in AT1 expression, but we cannot see an alteration in H2 expression in adrenal gland. But both of treatments reduced the expression of AT1 in the adrenal glands of diabetic mice, captopril and olmesartan, but we did not see any significant alteration in the expression of H2 receptor. And with this data, we can propose that the activation of angiotensin II AT1 receptor is involved to the increase in the corticosterone levels in diabetic mice. Okay, this is expected result because angiotensin II induces an upregulation of AT1. It's well known in the literature. Okay, and as I told to you, when we block it to AT1 receptor, the angiotensin II will activate the AT2 receptor. And we will look now to know if the activation of AT2 can participate that this down-regulated effect of olmesartan in the corticosterone production diabetic mice. For this, we co-treated the animals with olmesartan and a PD 123319 that is an AT2 receptor blocker. Okay, we use the two blocker, the H1 and the H2. And you can see first here on the plasma corticosterone levels that when we block the AT2 receptor, the effect of olmesartan disappear, okay? And we can conclude here that the effect of the blockade of AT1 receptor depends of the activation of the anti-inflammatory pathway signaling induced by the activation of AT2. However,
Travou?
O som desapareceu. Voltou.
apareceu. Eu não apertei, né?
Eu acho que agora voltou, gente.
Okay.
Okay.
I think it was some kind of fluctuation in our internet here, and I think it's right back on. No. It's
I looked at you
for
talking. Okay.
for the university.
Okay.
It's linked here in the cell phone as well.
Okay. Well, and we don't know yet how the mechanisms by the to reduce it is involved with this, but the activation of H2 appears to be involved to the effect of olmesartan. To confirm this, we treated the mice with a AT2 agonist, okay? And we used the CGP. And you can see that for the first time, a reduction in the fasting blood glucose, a significant reduction, but the animals is still hyperglycemic. But you can see a partial reduction of plasma corticosterone levels, and the AT2 agonists don't interfere with the increased expression of ACT8 receptor, star, and AT1 receptor in the adrenal gland, okay? And we can conclude until now that the inhibition of the angiotensin II synthesis by captopril and the blockade of AT1 receptor by olmesartan reduced the exacerbation of adrenal glucocorticoid steroidogenesis in diabetic mice, okay? And the activation of AT2 receptor also seems to be important to the olmesartan-induced decrease of adrenal glucocorticoid steroidogenesis in diabetic mice. And we will look at it for a third way of how inflammatory response or how inflammatory pathways can mediate the exacerbation of steroidogenesis by adrenal of diabetic animals. And now we will look for the TLR4 pathway. And you can see here how TLR4, because some cells of diabetic mice, type 1 diabetic mice like monocytes, have a high expression of TLR4. And because the activation of TLR4 is involved with the steroidogenesis in the adrenal gland, okay? And our first approach was look to the expression of TLR4. And you can see that here is a diabetic mice, but we reproduced all this data in diabetic rats in the same model, okay? But you can see that in a model with reducing the plasma insulin levels, hyperglycemia, and increasing the plasma corticosterone levels, we can see that there is no difference in the expression of some dumps that can activate toll-like receptor 4. For instance, we look to HSP70 and HMGB1, but we can see an increase in the expression of both toll-like receptor 4 and TRIF in the adrenal glands of diabetic mice. And I'm sorry, I think that yeah. Oh. I did not brought to you here, but in rats, we stimulated the animals with LPS, classic activator of Toll-like receptor 4, and the LPS inducing a great amount of glucocorticoid production by diabetic mice. And this indicates that this increase of Toll-like receptor 4 receptor are active Toll-like receptor 4 receptor, okay? And then we think about, okay, we have an increase in the Toll-like receptor 4 brief pathway expression, but we have an increase of some Toll-like receptor 4 activator in this animal. And we did not see this in some dumps that we looked for, but we think in look for some pumps, some exogenous pumps. And for this, we looked for the microbiota of in our model of diabetic mice. And you can see that there is no difference in the alpha diversity, but there is a difference in the similarity of the microbiota, the bacterial gut microbiota, okay? Not fungi, but we looked only to bacterial gut microbiota. But a difference in the similarity. And we reproduced some evidence looked in patients that a difference in the firmicutes, the abundance of the firmicutes, because have a difference in the ratio of firmicutes and bacteroidetes. I think it's called this, bacteroidate. But in diabetic patients, we did not see any difference in the bacteroidates. But with this data, we can see a difference in this ratio. And this is interesting because we see a great diversity of proteobacteria. The proteobacteria is one of the major class of the gram-negative bacteria and the pathogenic bacteria in the gut, okay? And you can see several species of bacteria higher in the higher diversity in our model, and other in the higher in controls, okay? And you can see some symbiotic bacteria higher in the controls, and several pathogenic bacteria higher in the diabetic mice, like Klebsiella pneumonia, Escherichia coli, and others. And here we can reproduce some data looked in the patients that dysbiosis with an increase in the abundance of pathogenic bacteria in our model of diabetes. And then we will look for the histopathological alterations in the column of our animals, and you can see here an increase in the villus height and an increase in the inflammation in the column of the animals, okay? Here we did an inflammatory scoring. And we looked to the mucus too, and you can see an increase in the mucus thickness and the PAS coloration. This is a little controversial because the high mucus production is known that can participate to the protection of the EIB barrier, okay? But the increase in the mucus production is not only the feature involved to this protection, because it's very usual to us to look in several tissues like lungs and also in the gut, that if you have inflammation, we will have the mucus production. And we believe that we are working here with a model with a leak of the epithelial barrier in the diabetic mice. And we will try to prove this then. But before, I will pay attention to the inflammatory status in the colon with some cytokines that we evaluate, not all, but some cytokines. You can see here a decrease in the levels of IL-1 beta, increasing the IL-10, and I will pay attention you to this triad here, the increase in the IL-17, IL-22, and TNF-alpha. This is one of the markers of a Th17 response, and the increase in the Th17 response is related to hyperpermeability of the epithelial-intestinal barrier. And then we'll look at for the epithelial-intestinal barrier. First of all, we inject by gavage one fluorescent marker in the fasting animals, and you can see that when we measured this fluorescent sound, an increase in this fluorescent sound in the blood of diabetic mice, and this attested that we have an increase in the permeability of the epithelial-intestinal barrier of diabetic mice. But when we looked for the plasma LPS, for our surprise, we looked at a decrease in the plasma LPS circulant levels in these mice. And we think that could be the time that we will look for the LPS, because this LPS could be spread to the tissues or for some tissues, and we will look for the suppression of LPS in adrenal gland. And you can see here in the right first, in the gut, in the colon, an increase in the expression of LPS, and this can suggest for us that in a little more time course for ahead, an increase in the LPS levels in the blood of in the serum or plasma of the mice, but more importantly is here. You can see a great expression of LPS in the adrenal cells in the zona fasciculata of diabetic mice, especially in the membrane of these cells, okay? And now we have both the increase in the expression of the receptor and the agonist. And how we can modulate this? We think modulate this with antibiotic therapy, okay? And we treated the animals with antibiotic therapy, and you can see a little significant, but still hyperglycemic profile in the diabetic animals. We did not see any alteration in plasma insulin levels, but we can see a drastic reduction of plasma corticosterone levels, and it was accompanied by a reduction in the expression of toll-like receptor 4 and 3. Okay, and this strongly suggests for us that the dysbiosis and the activation of toll-like receptor 4 pathway is involved in the increase in the glucocorticoid production by adrenal glands of diabetic mice. Okay, to confirm this, okay, the title is wrong, I'm sorry. And now we use two approaches to block it, toll-like receptor 4 activation to attest if the activation of toll-like receptor 4 is involved in the high production of corticosterone by adrenal glands of diabetic mice. First of all, we used toll-like receptor 4 antagonist, the TAC 242, if I remember good, I think it's 242. And we used another approach, and we induced diabetes in C3882 mice. These mice, they express toll-like receptor 4, but this toll-like receptor 4 is a mutant receptor in the LPS locus. And if we isolated macrophage and stimulate the toll-like receptor 4 with LPS, we did not see the activation of the cells in the in some concentrations of LPS. Okay, if you use the high concentration, very high concentration of LPS, we can see a jump in the mutation and the activation of receptors. It's not this case, this in vivo case here. And you can see that both the toll-like receptor 4 antagonists in the mutant animals did not interfere with blood glucose and plasma insulin levels, but both the toll-like receptor antagonists and the mutant mice present a reduction, significant reduction in the corticosterone levels, in the plasma corticosterone levels of diabetic mice. Okay, but here is very important. The mutant mice, they established the diabetes. And then we looked only for the toll-like receptor for antagonist, and you can see that the mechanism is pretty similar that the prevalence that I showed to you. A reduction in the steroidogenic pathway, reduction in the 11-beta-8-SD1, ACT8 receptor, and also a reduction in the toll-like receptor 4 and 3 expression in the adrenal glands of diabetic mice. And we can conclude here that in diabetic mice, we have dysbiosis in the gut dysbiosis in the colon, and an increase in the epithelial-intestinal permeability that close association with Th17 response in the local Th17 response. That LPS will in an influx of this LPS to adrenal glands that will activate the toll-like receptor 4, 3 pathway, steroidogenesis, and increase in production and release of glucocorticoid hormones. And is the last one. And in the last one is a previous results of our lab is in a project that we are starting in the lab to look for fatty acids, the effect of fatty acids in the steroidogenesis in diabetic mice. And we look now for long-chain and short-chain fatty acids. These fatty acids activated several FIOCRUZ receptors, and all of these receptors have anti-inflammatory properties. Okay, we will beginning this project looking for FIOCRUZ receptor because they have some anti-inflammatory properties, but the activation of this receptor is involved to the blockade of the toll-like receptor pathway too. Okay, and we looked for the expression of the FIOCRUZ receptor, and you can see a drastic reduction in the expression of this receptor of the adrenals of diabetic mice. And when we treated the animals with omega-3, omega-3 is not the better activator, but it's one activator of the FIOCRUZ receptor because the omega-3 have several other effects. Okay, but as I told you, it's a preliminary results of the project that we are starting in the lab. And you can see that the treatment with omega-3 reduced the expression, the plasma corticosterone levels in the diabetic mice. And it's a very, how can I say, it's the beginning, I said to you, it's the starting of the project, and it's a very partial conclusion of the project. That our results indicate that the adrenal of diabetic mice showed a lower expression of FIOCRUZ, and that omega-3 reduced this hypercortisolism observed in diabetic mice. If this depends or not of AR1 or 4, we need more experiments to elucidate this because it's still elusive for us and for literature. And I'm sorry, I talked too lot, but the conclusions here is that in diabetes, and in adrenal of diabetic mice or rats, in the balance, we have the balance pending to a pro-inflammatory pathway with a high activation of angiotensin 2 A2 pathway, LPS2 toll-like receptor 4 pathway, and less activation of anti-inflammatory pathways as PPAR gamma and apparently FFAR4 pathway, and this is responsible for the high production of glucocorticoid by adrenals. And now we will look into some effects of glucocorticoids too. And we will look into the effect of these treatments of the modulation of long-chain and short-chain fatty acids on the osteoporosis and the relationship with corticosteroid production, because we see that in this model, in this time, we have osteoporosis profile, because we have a low bone mineral density in several bones of the animals. Because now we have a new platform in the lab with a micro-CT, and you can look it for the bone mineral density too, okay? And I would like to thank all the team of Laboratory of Inflammation, especially the students involved in the project, Natalia, Bia, Fabiana, Débora, Amanda, Lucas, Lívia, all the financial support, and some collaborators, Luis Caetano Antunes, that he did all the microbiota analysis for us, and now to Ana Carolina from here for IBCCF, that will cooperate with us with the project of a long and short chain fatty acids. Okay, thank you a lot for you.
All right. Thank you very much, Vinicius, for this exciting talk. We are going to open questions for the students, and we already have one. So, Vanderlei, please, if you could come here so you can appear on camera. Thank you.
Right. Vinicius, thank you for your talk. Very interesting data. I just would like to know, I don't know if I missed some part of information. It was a lot of data. And in your experiment that you used the antibiotic, I just would like to know which time point did you start the treatment?
Thank you. I started the treatment 1 week after diabetic induction, and we put the antibiotics in the drink water, and they drink the antibiotics for 2 weeks. We used 3 antibiotics. I will remember here: ampicillin, metronidazole, and neomycin. Okay, one more student too. Oh.
Don't know if you have any other questions from students. We do have some comments in the chat. Okay. Well, actually, I do have a question for you. Well, actually, two. I would like you to comment a little bit more on the implications of these changes in glucocorticoids and how they would actually affect diabetics complications in these animals and eventually in patients. And other, you talked quite a bit about inflammation and how inflammation may play a role in the changes associated with diabetes. But was wondering if you have a inflammatory cell that you can pinpoint as playing a role in this process, or is there inflammatory infiltration in the adrenals? Is there some sort of resident population? What's going on in these inflammatory components?
Thank you, Bruno. And the first question, the glucocorticoid is involved in, as I told in the starting of the presentation, is involved in several complications or comorbidities, especially in the complications that involve in nervous system, peripheral and central nervous system, like neuropathy and the increase in the incidence of depression, and some authors show it that glucocorticoid is important to the development of the antidepressive therapy resistance, because the diabetic have 3 times more antidepressive resistant therapy than non-diabetic patients, and appears that the glucocorticoid pathways in neuroinflammation induced by glucocorticoids and the glutamate and signaling, increase the glutamate signaling, is myself, can be involved with these antidepressive resistant therapy. Okay, but some authors show that in the wound healing deficiency, the increase in the glucocorticoid can be involved with these deficiencies too. Okay, and in the neuropathy is the astrocyte activation is important for this glucocorticoid action to the words of neuropathy in diabetic animals. Okay. And about the inflammatory cells in the adrenal, we looked for neutrophils. When we look at in the AT stain, it's very difficult to see inflammatory cells. Okay, but unfortunately, I don't brought this here because it's a huge presentation. But when we performed the toll-like receptor for expression in the rats, we did this by immunohistochemistry. And we can see an increase in the cells like macrophages when we looked for the cells that express toll-like receptor 4. Several cells that I looked is like a macrophage, but we don't know yet if the macrophage can be involved in this. But it's well known that in the adrenal glands have macrophages, and from the embryonary production in the adrenals, and monocyte-derived macrophages. It's well known that adrenal has these, and this macrophage is involved in the aldosterone production, but appears not involved in the corticosterone production. However, we cannot affirm that is involved or not in the overproduction of glucocorticoids in diabetic mice. I have this to start this too, but I need students to start this project in the lab. But I think that's a good approach and can be explained this to your question. Okay.
Thank you. Miriam, please.
So Vinicius, thank you again for accepting our invitation. It's really, really beautiful data. And I know very close to nothing about diabetes, but what I wonder is, do you see these differences in glucocorticoid production if you try to control the diabetes, thinking that, let's say in a patient that has type 1 diabetes, it is already installed. So you mentioned it's not a good model for the beginning, but it's usual that they have a better control of glucose serum levels. And so the question is it related? Could it be related to the high glucose in the blood, or it is independent of that, or it's because of the long-term exposure for high and low, those peaks? Are you able to model that in the lab, or?
Okay, thank you. Yeah. Modulate glucocorticoid production to modulate the diabetes in type 1 diabetes is very difficult. It's not a point. We can think in some safe drugs that can also modulate glucocorticoid production and have an improvement in the treatment, because in type 1 diabetic patients, we have addressed, the patients, not we, but the patient have a drastic reduction in the insulin production, and we needed the insulin. It's not the question, but we can think in the patients can use a little less insulin, maybe, with some strategy that can modulate glucocorticoid production. This you can think that a diabetic patient that have hypertension, okay, these drugs that we use here, captopril and 8Bs, are very safe and can also reduce glucocorticoids and can be useful to the co-treatment with insulin. But if you think in type 2 diabetes, I think that can be a good strategy, because the glucose is not so high than in type 1 diabetic patients. And one of the mechanisms involved with the insulin resistance in the obese patients is the high glucocorticoid production. And if you can modulate this, you can modulate in some cases, because we can always think that the medicine is personalized, but in some cases it can be a help in the treatment in type 2 diabetic patients. Okay.
I have a question that I think sums up a lot of what Miriam asked and what Bruno asked. Do you think you can pinpoint maybe one of these targets, because you showed several great effects on reducing the hypercortisolism? So do you think you can pinpoint maybe one of these targets as maybe something that could also help other other consequences of diabetes, such as, do you think you can maybe help with wound repair, or like wound healing, or other things that are affected, that are due to the increased inflammation in diabetes patients?
Look, we think is this. We think that we can modulate the hormonal imbalance, especially here, the glucocorticoid production. We can modulate some complications that this imbalance is involved. Now, we will look for the bone mineral density, but we could look for the depression, we could look for Alzheimer, we could look for the neuropathy, okay? But we think that it can be an important target to, we looked for some diabetic complications in the patients. Okay?
All right. I guess we don't have any more questions, so I'll take this opportunity to once again thank Vinicius for this very exciting talk, for the kindness of coming here today to share some of his work with us. But I especially would like to thank the audience that joined us throughout this semester. And we are going to close shop for the semester. We're going to enjoy a well-deserved vacation of the immuno webinars. but we hope to have you all here together with us when we return in a few more weeks ahead. Also would like to thank Miriam, Cristiane, and Lucas from the Federal University of Rio de Janeiro for the help with the organization. And we also should mention Diego, Márcio, and Gustavo Amarante Mendes from the USP side of the organization of these immunowebinars. And we are hoping to have even greater participation of the SBI from the Brazilian Immunology Society Southeast Regional in the organization of the forthcoming conference. So guys, enjoy your vacations, enjoy some time off seeing my face in your computers, and we hope to see you again soon.